welcome to this explainer. Today, we're going to look at one of the most profound connections ever discovered between pure numbers and the very fabric of reality itself. We are exploring the Adelic Langlands pathway to the ABC conjecture. Now, I know that sounds daunting, but I promise you, this journey is absolutely incredible. We're going to see how translating the discrete, bounded nature of prime factorization into the structural convergence of an automorphic L function literally prevents spacetime from unraveling. Yeah, you heard that right. We're connecting simple addition and multiplication directly to the structural integrity of the universe.
To get us there, we've got a really tight, six-step, rigorous roadmap for today. We'll start with a macro view in the ABT tension, move to Frey curves and degeneration, then look at shattering global reciprocity, down into the rigid mechanics of phase locking and conductor bounds, semi-stable Satake parameters, and finally zoom all the way back out to physical reality with the space-time mass gap. All right, section 1, the ABC tension, or what we're calling the discrete challenge.
Okay, let's dive into this. It really all starts with a deceptively simple equation. A plus B equals C. But we're looking specifically at a trio of coprime positive integers, where A plus B equals C. The fundamental inequality of the ABC conjecture states that C is strictly bounded by the radical of the product of A, B, and C raised to the power of 1 plus epsilon multiplied by some constant. Now that radical, that term rad of A, B, C, is just the multiplicative product of their distinct prime factors. The historical difficulty here, the reason this is so tough, is that standard arithmetic geometry just really struggles to measure this specific gap. It's this fundamental tension between simple additive operations and multiplicative prime structures. Basically, how do you measure the exact boundary where addition and multiplication collide?
Moving right along to section 2, Frey curves and degeneration, where we map numbers directly to geometry.
So to actually solve this, we can't just stare at the discrete numbers. We have to map them into geometry. To apply the massive, heavy-lifting machinery of the Adelic Langlands Program, we need a geometric character. So we translate our additive equation into a Frey elliptic curve, EABC, defined over the rational numbers. And look at this. The exact Weierstrass model is y squared equals x times x minus a times x plus b. This is just a brilliant illustration, a true work of genius. By doing this, the arithmetic properties of the curve directly mirror our ABC numbers. The minimal discriminant of this curve, delta, is roughly equal to a times b times c squared. And its conductor, n, is exactly the radical of ABC. We've successfully packaged our discrete numbers into a geometric object living on the Adelic moduli stack, where the exceptional set of ramified primes are precisely the primes dividing ABC. Which brings us to section 3, shattering global reciprocity, the descent into chaos. Now, here's where things get, honestly, a bit mysterious and definitely a bit urgent. What happens if we assume the ABC conjecture is just false? Let's hypothesize a counterexample for a second. If we find a sequence of trios where C actually breaks the bounds, the discriminant of our Frey curve grows exponentially relative to its conductor. Geometrically, this means our curve develops this ultra-deep, infinite local stretch at those ramified primes. And as we try to pass this through spectral regularization, we encounter a totally catastrophic geometric consequence, the J-functional flow failure. The metric flow simply fails to converge. The curve's arithmetic volumes attempt to stretch infinitely, and that forces the metric tensor into an infinite curvature spike at those exceptional primes. It's literally like stretching a mathematical rubber band until the very fabric of space snaps. It becomes a violent, non-unitary phase rotation that completely distorts our local parameters.
And this local infinite spike, well, it's a massive problem because it violates a foundational law of our reality. As you can see here, the universal cosmic partition function enforces macrostability across the Adel ring via the global functional equation. You see, the universe absolutely requires global balance.
So what exactly happens when that infinite geometric stretch smashes into the global equation? Complete and utter disaster. Because the curve is stretched infinitely, the lower ramification groups fail to stabilize, and this forces the wild swan conductors to just balloon toward infinity. And if the swan conductors explode, the scaling exponent diverges. This immediately, violently destroys the automorphic character of the entire global partition function. The system can no longer close under scale inversion. It just shatters.
Let's pull back and look at section 4, phase locking and conductor bounds, the rigid mechanics.
But, as we all know, the universe doesn't just shatter, right? The universe behaves a lot like a self-correcting computer, one that explicitly vetoes this kind of analytical chaos. To protect the global functional equation, the system forcefully caps the geometric distortion. It does this via the Fourier Mukai transform acting directly on the prim fibers. Think of this almost like an arithmetic shock absorber. It takes that localized, wildly divergent energy from the infinite stretch and distributes it harmonically across the compact, complex prim torus. The off-diagonal curvature generates total destructive interference on the anomaly. It literally smooths away the infinite stretch and tames those wild swan conductors right back into bounded integers. We can actually see this rigid control playing out right here on the slide. If we look at the exact arithmetic derivation for the wild prime p equals 2, here is the rigorous two-adic setup. By applying the canonical Tate shift, where little x equals 4 big X and little y equals 4 big X plus 8 big Y, we rewrite the equation into a generalized Weierstrass form. This standardizes the two-adic valuations, and incredibly, it drops the minimal discriminant by a massive factor, literally 2 to the power of 12.
So the crucial point is, through Tate's algorithm, the Artin conductor exponent, F2, is classified into exact branches based on the two-adic valuation of B. Whether it's semi-stable, strongly non-monomial, or deeply wildly ramified, the exponent is rigidly locked to the exact integer bounds of 1, 3, or 5. The two-adic local field structurally prohibits a divergent error cascade. The universe mathematically refuses to let the conductor grow to infinity.
Moving into Section 5, Semi-Stable Satake Parameters and Local Weight Pinning.
To see exactly how tight these constraints really are, let's zoom into the semi-stable reduction blocks. When we map the local geometric invariance of the Tate curve to the Hecke stack under multiplicative reduction, we get the Steinberg representation. Now, this Sauté parameter matrix takes an exact, non-diagonal, unipotent layout. Notice the off-diagonal extension class there, and more importantly, look at our exact Sauté eigenvalues sitting right there on the diagonal. Now, why does this unipotent layout actually matter? Well, it comes down to the wild bounds. If an anomalous ABC trio tried to create that infinite stretch we talked about, it would have to compress these eigenvalues, forcing them toward infinity. But look at the formula. The unipotent architecture strictly pins the active eigenvalue to exactly p to the power of -1/2. It absolutely suppresses divergence, generating exactly 0 poles inside the critical strip. The mathematical anomaly is trapped, it's pinned, and it is neutralized for good. And that leads us to our final section, Section 6, the spacetime mass gap and global re-expansion. Now, what's really interesting about this slide is how we take this highly abstract, rigid microscopic math and see how it literally dictates the physical structure of our reality. In the Cohen's-Chemsedine spectral action principle, the physical mass gap squared is the first structural coefficient of the heat kernel expansion, and you calculate that directly by evaluating the log derivative residue of the universal partition function at its primary pole, s equals 1. By taking that derivative, this exact emergent spacetime mass gap formula isolates the arithmetic mass shift injected by our ramified prime set. If we compare our two scenarios side by side right here, the physical stakes become incredibly clear. On the left, if the ABC bounding envelope failed, the exceptional set blows up, and that emergent spacetime mass gap explodes to infinity. Spacetime literally shatters. But on the right, because of Fourier-Mukai phase locking and those rigid limits on our eigenvalues, the summation collapses into a highly stable, convergent arithmetic constant. The envelope constraints, they hold the mass gap together. And this brings us to the grand conclusion of this explainer, the physical veto of mathematical chaos. Physical mass gaps of emergent spacetime are topologically anchored by the additive multiplicative coherence of the integers. The universe forces the local L function eigenvalues down to their unipotent core, radiating the topological noise away. The ABC conjecture isn't just some abstract rule about numbers. It is an invariant reality of the Lagos field, ensuring that physical law emerges coherently. Which leaves us with a truly staggering thought to end on today. If the bounded geometry of pure integers directly dictates the stable mass of spacetime itself, what else about our physical reality is already written in the numbers?